This is the eighth and final lecture in our density management series, and we are going to discuss density management diagrams. Now, as you're familiar with this diagram, we've used this just for graphical illustration for size density relationship for stands of a given species. So this one is for lodgepole pine. And you can see the max SDI here. This boundary line is, in fact, that's the max SDI for lodgepole pine. Density management diagrams come in lots of different forms, variations, depending on where you're working. The one on the right is a standard format in British Columbia and other parts of Western Canada. The pretty complicated one on the left is from, that particular one comes from Spain. So they are typically for even-aged stands, and they're species specific. So again, this is for lodgepole pine. And what they represent is simple stand average models, and they're an example of a nomogram. So if you know two things, you can predict a third variable. So we're going to build up one. This is for ponderosa pine. So there's the max SDI for ponderosa pine of 450. And then some additional SDI lines, which are parallel to, of course, to the boundary line, just at convenient intervals. So we've got the logarithm of trees per acre on the x-axis, the logarithm of dq on the y-axis, and then our SDI lines. Now, if we have stands, many even-age stands of ponderosa pine, we can, with regression, we can predict site index, top height. So so-called site height. So the average height of the dominants and codominants, and plot that. Use the regression model to plot this family of curves. So ranging in this example from an average height of 20 feet up to 110. Similarly, we can use all of our stand data, and we could build another regression model that predicts total stand volume, cubic feet per acre, for example, given diameter and trees per acre, and we could plot those lines. And so here they are. We've got volume in cubic feet per acre ranging from a low of 100 up to 7,000 cubic feet per acre. So all of them together, we've got site height, we've got volumes, and it's a really busy diagram. It's very busy, but it has an awful lot of utility. So we're going to, one of the things that make them useful is that if we couple the density management diagram for the species that we're working with a set of suitable site index curves, we can assess time. So our density management regimes up to this point have been independent of time. They've all been based on size density, but now we can introduce time. So that's one of the advantages of the density management diagram. Now we're going to use it to, we typically use them to assess current conditions. So here's our simple, we haven't got any volume lines on this simple example of a density management diagram for lodgepole pine. But if we have a current stand that has a combination of mean size, looks like about 3.5 inches, and maybe 1,500 trees per acre, you see its SDI. Looks like the average height of the site trees is about 25 feet. And we can project alternative futures, for example, with and without thinning. just drawing, I mean, we say, well, this stand without thinning, the relative density is going to increase. It's going to get into the zone of imminent competition mortality and self-thin. So we could project this stand's future very simply graphically up to a top height of 80 feet. Alternatively, we could graphically simulate thinning. We could pre-commercially thin this stand and project it out into the future up to a top height of, again, 80 feet. So we could compare and contrast these two alternatives just very quickly, very simplistically. Density management diagrams are traditionally constructed for commercially important species. However, they're used for objectives other than simply timber. So this is a diagram for longleaf pine in the southeast, and we've got a young stand, and it's down here, a very small DQ, about 700 trees per acre. Here's a mature stand, over 16 inches in diameter, about 100 trees per acre. Such a diagram, one of the things that a diagram can be used for is managing for red-cockaded woodpecker habitat. And this gray area, this sort of blob here, the polygon, is the result of a combination of stand characteristics that wildlife biologists and others have come up with to characterize quality red-cockaded woodpecker habitat. And something like this is pretty useful in terms of managing. If I had a stand that was currently down here, I could project what would happen without intervention, as opposed to perhaps an early thinning that would get my stand into that red-cockaded woodpecker structure quickly, or more quickly than without intervention. This picture here, both of these stands are within that gray area, and both of them have red-cockaded woodpecker colonies. These two trees have been painted by the biologists because they're cavity trees. This is a density management diagram for Scots pine in Italy. And this example, which we'll go through quickly, is people have used this diagram to assess structure that would be appropriate for providing maximum rockfall protection. This is a big deal in some alpine valleys in the Italian Alps. People live at the bottom of the valleys. They park their Beamers at the bottom of and Audis at the bottom of the hill, and really don't like it if the chalet and the car gets squashed. So having protection forests that are going to minimize the risk of rockfall damage is an important consideration, and we're going to build that kind of up. One of the things that's been suggested is that canopy cover needs to be greater than 60%, and we can compute that from diameter crown width curves and plot that on the diagram. So that's the pink area. So we need to be above that pink area to meet this criterion of canopy cover greater than 60%. Another is the mean tree free distance. So this is the distance between trees, the spacing, and it has to do with the density of the trees and the boulder size and so on. And so that's been plotted on the diagram. Another thing that people have come up with is the live crown ratio. You've got to have a live crown ratio greater than 30%, and so that's plotted here. So we're losing our degrees of freedom. Another thing that's been suggested is a height diameter ratio. So if the trees are too slender, a tree hits them and they're just going to knock it over and keep on rolling. So we've got to have kind of stocky trees, and so some other people have come up with this height diameter ratio. So we plotted that on the diagram as well. And then finally, quadratic mean diameter greater than a third of the boulder size, and we superimpose that on the diagram. And basically, the authors of this paper have come up with two different polygons. There's minimum protection in this light gray area, and then maximum protection here. So in planning management of a Scots pine stand that is perhaps currently providing some protection, but we know that it's going to be losing that ability because of the way that trees grow. Maybe we'd want to schedule a timely thinning to keep the stand within that sweet spot as long as we could manage. So this is a fairly sophisticated example of the use of a density management diagram. A little closer to home, here's a lodgepole pine diagram again. In this case, we have both the volume lines and the height lines. And a paper by Anhold and his co-authors, he suggested that at this range, this polygon, trees an average diameter greater than 8 inches, and if the stand was not very open or not very dense, really was prime beetle habitat. So this is it was their contention that you wanted to, in your density management, wanted to avoid combinations of mean size and density that put you within that green polygon. Some other folks use the diagram to look at goshawk nest stands, and they said, well, the trees have to be greater than 10 inches on average, and they can't be too open, they can't be too dense. And so in this case, in planning for a goshawk nest stand, you wanted to be within that polygon. Superimposing those, it's interesting. The silviculturist hasn't got an awful lot of wiggle room here. You want to avoid the green and stay within the tan, and it's possible to do that, but it's going to require some pre-planning. This is a white bark pine density management diagram, and notice that the people that put this diagram together, rather than having lines corresponding to or labeled with the actual SDIs, they've just put max and then 60% of max and so on. So slightly different way to do this. One of the challenges, this is a limber pine that's been attacked by mountain pine beetle, but I didn't have a picture of white bark pine attacked. Mountain pine beetle is a concern. Now, Perkins and Roberts suggested that with white bark pine stands, you needed an SDI less than 80 in order to reduce the risk of mountain pine beetle outbreak within your stand, and so that line has been imposed here. That's 80%. That's 80, an SDI of 80, which is substantially less than 25% of the max. Another issue in managing white bark pine is making the Clark's nutcracker happy, and it's been suggested that in order to do that and maintaining resilience in this regard, you've got to have a threshold of cone production. Otherwise, the Clark's nutcracker will abandon that stand in that area. So, and they, based on some empirical work, they suggested that greater than or equal to 22 square feet per acre of mature live white bark pine is sort of a threshold. That's sort of a minimum that you have to have, a minimum stocking, minimum relative density that you have to have in order to keep the nutcracker engaged in the stand. Putting those two together, it really means that the silviculturist doesn't have an awful lot of room to work with. So we need to be above this line to keep the nutcracker engaged. We need to be below this line in order to keep the risk of mountain pine beetle outbreak at a low level. And so this is the area that you've got to work with in designing a density management regime. It's a pretty graphic display of that. So designing a density management regime with a density management diagram. This is an alternative to the calculator method that we've used. So let's go through a simple example. I've sort of changed. This is a stand that we've worked with before, but I've changed the numbers a little bit. And in addition, we've got a site index. So site index for lodgepole pine, base age 100 here, is 90 feet. Upper limit, we're going to assume we want to avoid self-thinning, so we're going to use an upper limit of 400. We're going to use a lower limit of 250, given this kind of an objective of full site occupancy. So it's about 36% of max SDI. An end of rotation DQ of 15 inches is our DFC, and we need a minimum DQ of 7 inches in order to have a commercially viable thinning. And we're going to assume, and we're relaxing that D over D of 1 assumption. We're going to simulate a low thinning, and the density management diagram allows us to do that. So the first thing that we do, we take that upper limit of 400, SDI 400, and we just draw a line there. The lower limit of 250, we draw a line there. So that's just very quickly we can do that. Now the DQ of 15 inches, we'll draw a line there. The threshold of 7 inches, we'll draw a line there. Okay, took us about 30 seconds to do that. We're going to start at the end of the rotation and work backwards. Okay. Now, as we work backwards, I want to point out to you that when we come down here, we don't go straight across. Okay, we're going to actually show that there's a lift when we thin. So here's the before thinning, here's the after, and that shows an increase in the average diameter of the stand after the thinning compared to before. So that's the so-called chainsaw effect. The trees didn't magically increase in size as a result of our thinning, but we were removing smaller than average trees. So that's the so-called chainsaw effect. And we can simulate that with the density management diagram because we've simply paralleled the site height lines. If you think about it, what do you do to the average diameter when you do a low thinning? Well, you increase it because you're removing smaller than average trees. What do you do to the site height? What do you do to the average dominant of codominance when you do a low thinning? And the answer is nothing. You don't touch those trees. They're the biggest ones in the stand, and in a low thinning, you're not changing the site height. So that's why this works. And in fact, it's a very realistic approximation of what the reality would be. So we worked our way all the way backwards. We've got a pre-commercial thinning, which we can do now. We can delay it. I mean, we can go through that whole thing. But whenever we do that thinning, we're going to be using it to set up this first commercial thinning. which sets up the second commercial thinning, which sets up the end of the rotation. Now, where does age come in? Well, we've got our site index curves. How old will the stand be at the end of the rotation? And we can calculate or estimate the age at the end of the rotation. We can estimate the age at this thinning, and so on. But let's do it for the end of the rotation. The density management diagram predicts that the average height of the dominants and codominants is going to be 85 feet. So do you see that? We're right here. We're above this 80-foot line. We're below the 90-foot line, and I've just graphically, ocularly estimated that's about 85 feet. Okay? And we've got a site index base age 100 of 90 feet. So we go to our site index curves, we find the appropriate curve. Here's the site index 90, base age 100 curve, and 85 feet, we come over to the curve and drop down and read the age. So it looks like we're just over 90 years, maybe 92 years at the end of the rotation. So scheduling the PCT, doing it now, doing it later, we can quickly look at those alternatives with the diagram. Before, when we were doing the calculator method, we went through the issue of we're really happy with that first commercial thinning, and I said, when in doubt, throw it out. Well, we can display that same kind of an alternative. I could imagine being in an ID team meeting and talking through some of these alternatives with other resource specialists. And in fact, if we were really being, we might, another alternative would be to do a very heavy pre-commercial thinning in order to set up the end of the rotation and forego these commercial thinnings. So this brings us to the end of our lecture 8 and the density management series, and you're going to get a great deal of use out of this material.